Hi, folks. Why don't we get started? Um, Welcome back. Good to see you all here. So I am going to first, we'll recap what we did last time and what we're going to do today. I'll talk a little bit about the problem set, and we'll also have a break as requested halfway through. So why don't we jump in? What we did last time was we introduced finite, besides introducing the course, we introduced finite automata and regular languages, which are the languages that the finite automata can recognize. We talked about these regular operations, and then building, those allow us to build what we call regular expressions. These are ways of describing languages. So we have finite automata can describe languages, and regular expressions can describe languages. And one of our goals is to show that those two systems are equivalent to one another, even though they look rather different at first glance. So to move in that direction, we first proved, we're going to prove closure properties for all of the, for the class of regular languages over these regular operations. So we'll show that, well, we already showed that any two regular languages have their union also being regular, and we'll show that for the other two operations as well. So let's just look ahead to what we're going to do today. We're going to introduce an important concept, which is going to be a theme throughout the course, called nondeterminism. And we are having that as a tool that we can use. We'll be able to show closure under concatenation and star, finishing up what we started to do last time. And then we'll use those closure constructions to show how to convert regular expressions to finite automata. And that's going to be halfway to our goal of showing that the two systems are equivalent to one another. And the following lecture, we will show how to do the conversion in the other direction. So I thought we would just jump in then and look at, return to the material of the course. As you remember, we were looking at the closure properties for the class of regular languages. We started doing that, and if you recall, hopefully, we did closure under union, and then we tried to do closure under concatenation, which I have shown here on the slide. You know, the proof attempt that we tried to do last time. And let's just review that quickly, because I think that's going to be helpful to see how to fix the problem that came up. So if you remember, we had we're given two regular languages, A1 and A2, and we're trying to show that the concatenation language, A1, A2, is also regular. And so the way we, the way we go about all of these things is, we assume that A1 and A2 are regular, so that means we have machines, finite automata for A1 and A2. We'll call them M1 and M2 that recognize A1 and A2 respectively. And then what we need to do in order to show that concatenation is regular is to make a finite automaton which recognizes the concatenation. And we tried to do that last time. If you remember, that concatenation machine, M, we're calling it, what is it supposed to do? It's supposed to accept its input if it's in the concatenation language. And that means that the input can be split into two parts, X and Y, where X is in the A language and Y is in the B language. Y is accepted by M1 and X is accepted by M1 and Y is accepted by M2. Sorry, I garbled that up. So X should be in A1 and Y should be in A2. If you can split W that way, then M should accept it. So M has to figure out if there's some way to split the input so that the first machine accepts the first part, the second machine accepts the second part. And the idea that we came up with for doing that was to take these two machines, build them into a new machine M, and then connect the accepting states for M to the start state, connect the accepting states for M1 to the start state for M2, Because the idea would be that if M1 has accepted an initial part, then you want to pass control to M2 to accept the rest. But as we observed, that doesn't quite work, because the first place to split W after you have found an initial part that's accepted by M1 may not be the right place, because the remainder may not be accepted by M2. You might have been better off waiting until you found another place that M1 accepted later on in the string, say over here. And then by splitting it over there, then maybe you do successfully find that the remainder is accepted by M2. Whereas if you tried to split it, the first place, the remainder wouldn't have been accepted by M2. So all you need to do, M has to know, is there some place to split the input so that, you can get both parts accepted by the respective machines. The problem is that M might need to know the future in order to know where to make the split. And it doesn't have access to the future. So what do we do? So what we're going to do is introduce a new concept that will allow us to basically get the effect of M1 in sort of being able to see the future. And that new concept is going to be very important for us throughout the term. It's called nondeterminism. And so we're going to introduce a new kind of finite automaton called a nondeterministic finite automaton. And first we'll look at that, and then we'll see how that fits in with the previous deterministic finite automaton that we introduced last time. So here's an example. Always good to start off with an example. Here is a picture of a nondeterministic finite automaton. Looks very similar at first glance to the former kind, the deterministic finite automaton. But if you look a little carefully, you see that there are some key differences. The most important difference is that in state Q1, for example, whereas in the machines that we introduced last time, there had to be exactly one way to go on each possible input symbol, so you knew how to follow along through the machine as it's computing. Here there are two ways to go. In Q1, you can either stay in Q1 or you can go to Q2. That's the essence of nondeterminism. There could be many ways to proceed. And furthermore, on Q1, if you get a B, then there's nowhere to go. So that's also possible within nondeterminism. There could be, so let's just start looking at these features. There are multiple paths forward, but multiple paths possible. You might be able to have one, as we had before, or many ways to go at each step, or maybe zero ways to go at each step. Those are all legitimate for a non-deterministic machine, which is doing a non-deterministic computation. Another difference, if you look carefully, is that we're allowing here the empty string to appear on a transition. That's perhaps a little less essential to the spirit of non-determinism, but it's going to turn out to be a convenience when we actually apply non-determinism to build machines, as you'll see very shortly. Now, if there are many different ways to go, some of those ways to go might have different outcomes. As we remember from before, we accepted the input if you end up in an accept state, and we rejected the input if you end up not in an accept state, in a non-accepting state, then you reject. But now there might be several different ways to go. And we'll do an example in a minute, but there might be several different ways to go, and they might disagree. Some of them might accept, other ones might reject, and so then what do you do? Well, in that case, acceptance always overrules rejection. That's the essence of non-determinism, the way we're setting it up. You may ask why that is, and sort of the spirit of that will become clear in due course. But right now, just take it as a rule. When we're having a non-deterministic machine, acceptance overrules rejection. So as long as there is one accepting one of the possible ways to go ends up at an accept, we say the whole thing is accepted. The only way it could possibly reject if all of the possible ways to go end up at a rejection, end up at a non-accept state. So we'll see example. I think we're going to do an example right now. Yeah. So if we take, for example, this machine N1 now on an input AB, and we're going to process the symbols one by one, just like we did before. But now, to follow along, there might be several different ways to go. So if we take the first symbol A, and we run the machine, so the machine starts at the start state as before, but now an A comes in, and there might be there are two different ways to go. So we're going to keep track of both of them. After the machine reads an A, you can think of it as being in two states now simultaneously. It can be in state Q1 and it can be in state Q2. So those are two different possible places it could be at this moment. Okay. Now we read the next symbol, the B. And from a B, you take each of the places where the machine could be at the end of the previous symbol, and you then apply reading a B, the next symbol, to each of those, from each of those states where the machine could be in from the previous symbol. So the machine could be in Q1 and Q2 after reading an A. Now we apply a B. Well, Q1 on a B goes nowhere. So you think of that a branch, if you will, of the computation as just dying off. It has nowhere to go. It just vanishes. However, when you're in the other possibility, which was state Q2 on a B, does have a place to go. So that the machine is now going to go from Q2 to Q3 when on that branch of the computation, which reading a B. And then it has coming out of Q3, there are two symbols. There's an A and an empty string symbol. Now on an A, the machine would have to read an A in order to transition along that arrow. But when there's an empty symbol on the arrow, that means the machine can go along that arrow for free without even reading anything. As long as it gets to Q3, it can automatically jump to Q4. And so once it has read a B and gone to Q3, now it can either stay in Q3 or it can go along the empty transition and go to Q4. So again, there's going to be a non-deterministic step at this point. The essence of having a empty transition is that there's going to be non-determinism. That's why we didn't introduce that for deterministic automata, because you don't have to transition along an empty string transition. You can stay where you are, or you can go along the empty string transition without reading any input and go over to the next state, which in this case is Q4. So let's just see where we are. After reading an A, we're in states Q1, Q2. But now after reading a B, we're in states Q3 and Q4 as possibilities. And now we're at the end of the input, and we look and see what we got. If any one of the states as possibilities that we are right now at the end of the string is an accept state, then we say overall the machine has accepted. So that corresponds to what we said over here before: accept the input if some path leads to an accept. So if any way of proceeding through these non-deterministic choices will lead you to an accept, then you will say we're going to accept the input. Okay, so this input here is accepted. Let's do another example. Suppose we have the input AA instead of AB. So AA, after the first A as before, we're in states Q1 and Q2 as possibilities. Now we read an A again. Now the one that's on state Q1, that possibility, Q1 possibility, after reading an A, it again branches to Q1 and Q2. So when we know after reading the second A, we're going to be in at least Q1 and Q2. Now, how about the state that had been, on Q2 on reading an A? The one from before, after reading the first A, you were in Q2. Now reading the second A, there's nowhere to go. So that one just gets removed. So after reading AA, we remain in states Q1 and Q2 as possibilities. Neither of those are accept states. So therefore, on input AA, the machine rejects. Okay? Let's just do a couple more, and then I'll ask you to do one. So we have ABA as an input. Let's see what happens then. So we have remember, after reading AB, the machine is in the two states Q3, Q4 as possibilities. That's what we had from the first example. So after reading AB, we're in states Q3, Q4. Now we read another A. The Q4 on an A has nowhere to go. In fact, it has nowhere to go on any input. So no matter what comes in after you're in state Q4, that branch dies. But on Q3, which is another one of the possibilities reading an A, it can follow along just transition, because that's one of the labels on that transition is A. So you can follow along just the transition when reading an A, which is the last symbol in the string. And so now after ABA, you are in only state Q4 as a possibility, but that happens to be an accept state, so the machine accepts. Okay, and now lastly, what happens, let's take our final examples. What happens if we have ABB? So, you know, as we remember before, when we were, after reading AB, that was the first example, we were in states Q3, Q4 as possibilities. Now we read a B. Well, neither of those states have anywhere to go on a B. So now all threads, all branches of the computation die off. And at this point, the machine is totally dead. It has no active possibilities left. So certainly it's going to reject this input, because none of the active states, there are no active states, are accepting states. And in fact, if you looked at anything that came later, anything that extended the string ABB would also be rejected, because once the machine had all possibilities have died off, there's no way for them to come back to life on any extensions. So with that, here's an important point before I'm going to jump to a check-in on you. I think one thing that might be on your mind about this non-determinism is how does that correspond to reality? Well, it doesn't. We're not intending for non-determinism as we're defining it to correspond to a physical device. But nevertheless, as you'll see, it's a very mathematically useful concept, this non-determinism, and it's going to be playing a big role throughout the subject as we'll experience it during the rest of the term. So with that, I'm going to have a little check-in. I'm going to ask you to consider what happens on one of the inputs. So here we go. What does it do on input AAB? So here's the machine. You can look at it, and hopefully there's a poll here for me to give to you. So you can give me your input. So what does the machine do on input AAB? Most of you have answered. Again, you're not going to be penalized for getting the wrong answer, but hopefully you'll get the right answer. Anyway, let's just take a look here. So time is up. Let's end the polling and share the results. So the majority have gotten the correct answer, which is A. The machine does accept AAB because when you have A, so if you like, I'll show you the path that corresponds to accepting. You go A, B, and then empty string. And so that sequence of steps is one of the non-deterministic possibilities that the machine can follow. And that shows that the machine does accept the input AAB. You could think about it the way we did it before. Also, if you read an A, it's in the two possibilities Q1, Q2. You read a second A, again in the possibilities Q1, Q2. Now you read a B, it's into possibilities Q3, Q4, and that's it. AAB. So now you read the B, it's in possibility Q3, Q4. Q4 is an accepting state. That overrules the non-accepting state, and so the machine accepts. You have to understand this. So if you didn't get it right, go back and think about where you slipped up, okay? Because this is, this is just getting, we're just getting warmed up here. It's going to get a lot harder. Okay, so stop sharing the results, and so let's continue. So now, just as we did last time, we can formally define a non-deterministic finite automata. Here's the picture again. Okay, so it looks a lot like the case we had before, the deterministic finite automata, or DFA, as we'll call them. It's a 5-tuple, so I've sort of written down little reminders for what those components of that 5-tuple are, that list of five components. So they're all the same as before: states, alphabet, transition function, start state, and accepting states. So that the formal definition looks exactly the same, except the structure of the transition function. So now, before, if you remember, you had a state and an input symbol, and you got back a state. Now we have something more complicated looking. We have a state and an input symbol, but it's instead of just sigma, it's sigma sub epsilon, and that's a shorthand for sigma union epsilon. And that's my way of saying that you're allowed to have on your transition arrows either an input symbol or an empty string. So the transition function has to tell you what to do when you have empty string coming in as well. So that would be part of your table for the transition function. Now, over here, what's going on over here? Well, now, instead of just producing a single state, when you've read, for example, an A from Q1, there's a whole set of possibilities. So here we have what's called a power set. That's the set of subsets of the collection Q. So here we're going to produce an entire subset of states. Instead of just one state coming out, there might be a subset of possible states that you can go to. So the power set of Q is a set of subsets of Q. So that's what this notation means. Again, this is something that I'm hopefully presenting to you as a bit of a reminder. You've seen this somewhere else before, but please make sure you understand the notation going forward, because we'll be doing less hand-holding as we start moving forward. Okay, so just let's take a look. The N1 example here, just to illustrate what's going on. When you're in state Q1 reading an A, now you get a whole set of possibilities, which in this case is Q1 and Q2. Whereas if you're reading a B, what would be that set? Coming out of Q1, what's the set of possible successor states? Well, there are none, so it's the empty set. Okay, so this is, hopefully you're understanding the notation here. So now here's, I think, really important. How do we understand non-determinism intuitively speaking? And there are multiple different ways which each has their value under different circumstances. So one way is thinking about non-determinism as a kind of parallelism. So every time the machine has a non-deterministic choice to make, where there's more than one outcome, you think of the machine as forking new threads of the parallel computation at that stage, where it makes entire copy of itself when there's a choice of possibilities. And then each of those independently proceeds to read the rest of the input as separate threads of the computation. So if you're familiar with parallel computing, this should be reasonably familiar to you. The only key thing to remember is that as this thing forks a number of possibilities, the acceptance rule is that if any one of those possibilities gets to an accept at the end of the input, it raises a flag and says accept, and that overrules everybody else. So acceptance dominates. So another way of looking at it is the mathematical view, where you can imagine, and we're going to use all of these, so you really need to understand them all. The mathematical view is, you can think of the computation as kind of a tree of possibilities. So you start off at the very beginning, sort of at the root of the computation, which is when it really begins. But every time there's a non-deterministic branching that occurs, the tree has, that node of the tree has multiple children coming out of that node. And so the different threads of the computation correspond to different branches of that tree. And now you're going to accept if any one of those branches leads to an accepting state. Okay, obviously somewhat similar to what we had before, but I think it's a little bit of a different perspective on what how to think about non-determinism. And the last one is going to sound a little weird, but actually I think for people who are in the business, it's the one they use the most. And that's the magical way of thinking about non-determinism. And that is when the machine has non-deterministic choices to make. You think of the machine as magically guessing the correct one at every stage, and the correct one being the one that will eventually lead it to accept. Okay, so you can think of the machine as guessing which is the right way to go. And if there is some right way to go, it always guesses right. Of course, if the machine ends up rejecting because there is no right way to go, then it doesn't matter. There is no good guess. But if there is some good guess, we'll think of the machine as taking that good guess and going that way. Okay. So now here is a very important thing. We introduced this new model, the non-deterministic finite automaton, NFA. It turns out to be, even though it looks more powerful because it has this non-determinism, it isn't any more powerful. It can do exactly the same class of languages, the regular languages. And we'll show that with this theorem here, that if an NFA recognizes A, then A is regular. We'll prove that by showing how to convert an NFA to an equivalent DFA, which does the same language. So we can take an NFA that has a non-determinism and find another DFA which doesn't have non-determinism but does the same language. It accepts exactly the same strings, even though it lacks that non-deterministic capability. This is going to be extremely useful, by the way, for example, in showing that closure under concatenation. Okay, so in this presentation here, I'm going to ignore the epsilon transitions, because once you get the idea for how to do this, you could figure out how to incorporate them. They just make things a little more complicated. So let's just focus on the key aspect of non-determinism, which is that the machine could have several ways to go at any point in time. There could be several next states on an input. Okay? Now the idea for the construction, so we're going to start with a non-deterministic machine M, and we're going to build a deterministic machine M prime, which does exactly the same thing. And the way M prime works is it's going to do what you would do if you were simulating M. What would you do? I mean, this is what we were doing as I was explaining it to you. If you were simulating M, every time you get an input symbol, you just keep track of what is the set of possible states at that point in time. That's what the DFA is going to do. It's going to have to keep track of which possible set of states the NFA could be in at the point on that input where we are right now. And then, as you get the next symbol, the DFA is going to have to update things to keep track of the next set of states the NFA could be in at this point, just like you would do. Okay, and so here's a kind of a picture, and how do we implement that so here's the NFA that we're starting with M, and we're going to make here the DFA, but in order to remember which set of states that DFA could be in at a given point. So maybe it's in the set of states that M could be in. Did I say that wrong? Which set of states the NFA could be in at a given time. So maybe M, the NFA, could be in at some point state Q3 and Q7. The way the DFA keeps track of that, it's going to have a state for every possible subset of states of the NFA. That's how it remembers which subset of states the NFA is in. That's the way DFAs work. They have a separate state for each possibility that they need to keep track of. And the possibilities here are the different subsets of states that the NFA could be in at a given point. Okay, so corresponding to this subset, to these two possibilities, Q3, Q7, the DFA is going to have a state with the subset Q3, Q7. And it's going to, for every possible subset here, there's going to be a different state of M prime. So M prime is going to be bigger. Okay, so quickly, the construction of M, the states of M prime now, Q prime, are going to be the power set, the set of subsets of states from the original machine M. Now we have to look at how the transition function of the DFA, I mean, the primed machines are the DFAs, the DFA machines. So these are the deterministic components. So delta prime, when it has a subset that, you know, something like this has one of its states which corresponds to a subset of states of M, and it reads an input symbol. You just have to do the updating the way you would naturally do. You're going to look at every state in R, look at where that can go under A. So there's a bunch of sets there, and look at all the possible states that could be in one of those subsets. And that's the set of states that you could be in. That's going to be the new set of states, and that's going to be the new state of M prime. Okay, so it's going to be the subset corresponding to all of the states that could be in when you apply the transition function of the non-deterministic machine to one of the states in the subset of states that the non-deterministic machine could be in. Okay, it's a little bit of a mouthful. You know, you could. I suggest you look at this if you didn't quite get it after the fact. Good to understand. The starting state for the NFA, for the DFA, I'm sorry, is going to be which subset now we're going to start off with. It's going to be the subset corresponding to just the start state of M. And the accepting states are going to be, of the deterministic machine, are going to be all of the subsets that have at least one accepting state from the NFA. Okay? So I hope you got that, because I'm going to give you another little check-in here, which is I'm going to ask you, how big is M prime? How many states does M prime have? I told you what those states are, so just go think about that. So check-in 2, if M has n states, how many states does M prime have by this construction? Okay, so let's launch the next poll. Okay, 5 seconds. And I think we're almost done here. Good. All right, share results. I don't know if sharing results is a good thing. I'm not trying to make you, if you didn't get the right answer, because most of the people did get the right answer. If you didn't get the right answer, trying to make you feel bad, but I do think you should, it's a little bit of suggestion, you know, that you need to review some basic concepts. So the basic concept here is, if you have a collection, if you have a set of states, how many subsets are there? And the number of subsets is going to be exponential. So if you have a collection of n elements, the number of subsets of those n elements is 2 to the n. That's the fact we're using here. And that's why M prime has 2 to the n states, if M had n states. And that's, you know, you should make sure you understand why that is. All right. So with that, as requested, we're going to have a little break. And that break is going to last us exactly 5 minutes. So we will return in 5 minutes. I'm going to be prompt. So I gave you a little timer here. So please, I'm going to begin it right when this is over. Okay. Almost ready. I hope you're all refreshed and ready for the second half. So now that we have non-determinism, we're going to use that as a tool to prove the closure properties that we were aiming for starting from last lecture. Okay, so remember, let's look at closure under a union. Now, we already did that, but I'm going to do it again, but this time using non-determinism, and you'll see how powerful non-determinism is, because it's going to allow us to do it kind of almost with no effort. We'll start off the way we did before. I'm going to start off with two DFAs, but actually these could be NFAs even. But let's say we started with the two DFAs for the two languages, A1 and A2, and we're going to construct the NFA. Now we're going to construct an NFA recognizing the union. And that's good enough because we already know that we can convert NFAs to DFAs, and therefore they do regular languages too. Okay, so now here are the two DFAs that do the languages A1 and A2. And what I'm going to do is I'm going to put them together into a bag of states, which is going to be M, the NFA that's going to do the union language. So remember, what does M supposed to do? M is supposed to accept its input if either M1 or M2 accept. So how is it going to do that? What it's going to do, we're going to add a new state to M, which is going to branch under epsilon transitions. And now you can start to see how useful these epsilon transitions are going to be for us. Going to branch under epsilon transitions to the two original start states of M1 and M2. And we're done. Why? Well, now, non-deterministically, as we get an input, W coming in to M, M at the very beginning, even just right after it gets going, the very first thing that happens is it's going to branch to M1 and also branch to M2 non-deterministically as two possibilities. And then inside M1 and M2, it's going to actually start reading the input, and each one is going to be now following along as it would have originally, the states corresponding to reading those input symbols. And M, as a combination of M1 and M2, is going to have a possibility for one state in M1 and one state in M2. And so M is going to have those combined into one package. And now if either, at the end of the input, if either of these end up at an accepting state, then M is going to accept as a non-deterministic finite automaton, because that's how non-determinism works. You accept if any one of the branches ended up accepting, which is just what you need for for union. So when we're doing union, we want either one of these to be accepting, and the non-determinism just is built conveniently to allow us to do the union almost, for free. So you can, again, thinking about non-determinism as terms of parallelism, you could think of it, the non-deterministic machine is running in parallel M1 and M2 on the input. And if either one of them ends up accepting, M will accept. Or you can think about it in terms of that guessing that I referred to before, which means that as M is getting, when it's just about to read the first symbols of its input, it guesses whether that's going to be an input accepted by M1 or an input accepted by M2. And the magic of non-determinism is that it always guesses right. So that input happens to be an input that's going to be accepted by M2. M is going to guess that M2 is the right way to follow, and it's going to go in the M2 direction. Because non-determinism, the magic is you always guess right. Wish that was true in real life. Would make exams a lot easier. Anyway, so now let's see how we can use that to do closure under concatenation. Okay, so now we're going to actually have a picture very similar to the one we had originally, but now using non-determinism, we can make it work. So here we have the two machines doing the two languages, A1 and A2, and we're going to combine them into one bigger machine, M, as shown. Remember, what M is supposed to do is accept its input if there's some way of splitting that input such that the first half is accepted by the M1 and the second part is accepted by M2. Way we're going to get that effect is by putting in a empty transitions, epsilon transitions, going from the for the accept states of M1 to the start state of M2, just as I've shown here in this diagram. So these were the original accepting states of M1, and now they're going to be declassified as accepting states, but they're going to have new transitions, empty transitions, attached to them, which allow them to branch to M2 without reading any input. And so intuitively speaking, this is going to do the right thing, because once M1 has accepted some part of W, then you can non-deterministically branch to M2, and you're going to start processing inside M2. And the point is I kind of jumped ahead of myself, is that the reason why it fixes the problem we had before is that the epsilon transitions your machine does not have to take them. It can stay where it is as one non-deterministic option, or it can move along the epsilon transition without reading any input as another non-deterministic option. So it's using this non-determinism now to both stay in M1 to continue reading more of the input and to jump into M2 to start processing what might be the second half or the second part of the input, which M2 accepts. And you can think of it in terms of the guessing, is that the machine is guessing where to make that split. Once it found an initial part that's accepted by M1, it guesses that this is the right split point, and that passes to M2, but there might be other guesses that it could make, corresponding to other possibilities. And so with non-determinism, it always guesses right. If there is some way to split the string into two parts accepted by M1 and M2, the machine will make that good guess, and then M1 will accept the first part, and M2 will accept the second part, and we'll get M accepting that whole string altogether. And so that is the solution to our puzzle for how do we do closure under concatenation. Okay, I hope that came through, because this is we're just getting going with non-determinism. We're going to be using non-determinism a lot, and you're going to need to get very comfortable with it. Okay. Now let's do closure under star. And closure under star works very similarly. But now we're just going to have a single language. If A is regular, so is A star. So they're not a pair of languages, because a star is a unary operation applying to just a single language. So if we have a DFA recognizing A, in order to show that A star is regular, we have to construct a machine that recognizes A star. And the machine we're going to construct is, as before, an NFA. Okay? So here is M, the DFA for A, and we're going to build an NFA, M prime, that recognizes A star. And let's think now, what does it mean to recognize A star? So when should M, if I'm going to give you an input, when is it in the star language? What does M prime have to do? So M prime, remember what star is. Star means you can take as many copies as you like of strings in the original language, and that's in the star language. So to determine if something's in the star language, you have to see, can I break it up into pieces which are all in the original language? So you want to see, can I take my input, W, and cut it up into a bunch of pieces, 4 in this case, where each of those pieces are members of A, they're members of the original language. So that's what M prime's job is. It has its input and wants to know, can I cut that input up into pieces, each of which are accepted by the original machine, M. That's what M prime does. And if you think about it, a little bit, really what's happening is that as soon as M, so, M prime is going to be simulating M. That's the way I like to think about this, as having M inside. So, you're going to run, if you were going to be doing this yourself, you're going to take W, you're going to run it for a while, you'll see, oh, M is accepted. Now I have to start M over again to see if it accepts on the next segment. So every time M accepts, you're going to restart M to see if it accepts another segment. And so by doing that, you're going to be cutting W up into different segments, each of which is accepted by M. Of course, it's never totally clear whether you should, for any given segment, you should cut it there, or you should wait a little longer and find a later place to cut. But that's exactly the same problem that we had before with concatenation. And we solved it using nondeterminism, and we're going to solve it again using nondeterminism. So the way we're going to get that effect of starting the machine over again once it's accepted is by adding in epsilon transitions that go from the start states back to from the accept state back to the start state. So now every time M has accepted, it has an option, not a requirement, but it has an option. It can either stay continuing to process, or it could restart, making a cut at that point and trying to see if there's another segment of the input that's going to be that it's going to accept. And this is basically the whole thing, with one little problem that we need to deal with, and that is we need to make sure that M prime accepts the empty string, because remember, the empty string is always a member of the starred language. And as it's written right now, we're going to be requiring there to be at least one copy of at least one segment. We're not taking into account the possibility of no segments, which is the empty string. And the way we're going to get that is, well, I mean, one way to get to add, so we're missing the empty string right now. So how do we fix it? Basically, we're just going to take the construction we have, on the screen, and we're going to adjust it to add in the empty string because it's possibly missing. One way to do that, which is tempting but wrong, is to make the start state of M an accepting state for M prime. So we could have made this an accepting state too. And now M prime is also going to accept the empty string. That's the good news. The problem is that the start state might be playing some other role in M besides just being the start. There might be times when M comes back to the start state, later on, and if we make the start state the an accept state, it's going to suddenly start accepting a bunch of other things too, which might not be intended. So it's a bad idea to make the start state an accept state. Instead, we'll take the simple solution alternative of adding a new start state, which will never be returned to under any circumstances, and make that a new start, an accept state as well. So here we'll have to make this additional modification. So as I'm saying, this is what we need to do. And the way we'll do that is by adding a new start state, which is also an accept state, to make sure it accepts the empty string. And then that also can branch to start off M as before, if the string that's input is not the empty string. And so then M, M prime is actually going to have to do some work to see if it can be cut up as it was doing before. That's the proof of closure under star. I'm not going to do it anything beyond what I've just described. These proofs by picture are convincing enough, I hope. And if not, they are explained in somewhat more detail, somewhat more formally in the textbook. But for the lecture, this is where I'm going to stop with these two arguments. And so now, one quick check-in on this. So if M has n states, how many states does M prime have by this construction? So let's do, really, these are, I'm not intending these to be very hard, more just to keep you awake. So how many states does M prime have? Okay, maybe a little too easy even for a check-in. Yeah, everybody's getting this one. Because all you did was we added one new state. So the answer is, as you have, I think pretty much everybody is observing, that it's just the, it's number B. So I'm going to end the polling. I'm going to share the results. And everybody got that one. And so let's continue on. The very last thing we're going to do today is show you how to convert regular expressions to NFAs. Thereby showing that every language that you can describe with a regular expression is a regular language. On Tuesday, we'll show how to do the conversion in the other direction, and thereby showing that these two methods of describing languages are equivalent to one another. So here's our theorem. If R is a regular expression and A is the language, is a set of strings that regular expression describes, then A is regular. Okay. We're going to show how to convert. The strategy is to convert R to an equivalent NFA M. And so we have to think about, remember these regular expressions that we introduced last time. These are these expressions that look like, A, B, union B, star, something like that. So built up out of the regular operations from the primitive regular expressions that don't have any operations, that we're calling atomic. So if R is an atomic regular expression, it just looks like either just a single symbol or an empty string symbol or an empty language symbol, or R can be a composite regular expression. Whoops, we're having a little, yeah, so we have two possibilities here. R is either atomic or composite. And so let's look at what the equivalent expression is in each case. So if R is just the single letter regular expression, that's a totally legitimate regular expression, just a regular expression 1. So that just describes the language of the string 1. So we have to make an NFA which recognizes just that language. It accepts only the string 1. So it's a very simple NFA. It just starts in the start state, and on that single symbol, it branches to an accept state, and there were no other transitions allowed. So if you get anything else coming in besides that one, that string, which is just that one symbol, the NFA is going to reject it. Like if it's too long, if it gets AA coming in, well, there's nowhere to go from this accepting state on an A, so the machine is just going to die. It has to be in an accept state at the end of the input. How about, why don't you think for yourself for a minute, how do we make an NFA which accepts only the empty string and no other strings? You can do that with just one state with an NFA, just this one here. The machine is going to start off in the start state, which is also immediately an accept state, so it accepts the empty string. But if anything else comes in, there's nowhere to go when the machine dies. So this machine accepts just the empty string, or its language is the language with one element, the empty string. How about the empty language? Well, here's an NFA which has no accepting state, so it can't be accepting anything. Now, if we have a composite regular expression, we're already finished, because we showed how to build up. We showed constructions which give us closure under union, concatenation, and star. And those constructions are going to enable us to build up the NFAs that do the language of these more complex regular expressions, built up out of the NFAs that do the individual parts. So if we already have NFAs that do R1 and R2, then the closure under union construction gives us an NFA that does R1 union R2 as a language. So I'm going to do, I hope that's clear, but I'm going to do an example which will hopefully illustrate it. And it's going to show you, basically what I'm giving you is an automatic procedure for converting a regular expression into an equivalent NFA. So let's just see if that procedure in action, which is really just following this recipe that I described for you. So here is a regular expression, A union AB, star. So this is a regular expression. It's some language, whatever it is, I don't care. But I want to make an NFA which recognizes that same language. And the way I'm going to do that is first build NFA for the components, the sub-expressions of this regular expression, and then combine them using our closure constructions to be NFAs for larger and larger sub-expressions until I get the NFA that's the equivalent of the entire expression. So let's just see how that goes. So the very most primitive parts, the smallest sub-expressions here are just the sub-expressions for A and for B. So here's the one for A, just for A. So this is the NFA which recognizes the language which is just the one string A. Here's the NFA for whose language is just the one string B. And now I want an NFA which accepts only the string AB. Now, of course, you could just do that by hand yourself. It's simple enough. But what I'm arguing is that we can do this automatically using the closure construction for concatenation, because really there's a hidden concatenation symbol. This is the A concatenate B. So now for AB, I'm going to take the thing from A and the part from B. So these two things that I had from before, and use the concatenation construction to combine them. You see that? So now I have automatically an NFA which does the language whose string is just AB, just the AB string. And it's not the simplest NFA. You can make a simpler one, but the virtue of this one is that I got it automatically just by following the closure construction. So now I'm going to do a more complex one, just the inside here, A union AB. So the way I'm going to build that is from the two parts, the A part and the AB part. The A part and the AB part. So here is the A part. Here's the AB part. I've already got those from before. It's really kind of a proof by induction here, but I think it's simple enough. We don't have to use that language. So we have, the A part, the AB part, and now we are going to apply the closure under union construction to combine those into one machine. And remember how that worked. We add a new symbol here, which branches under empty string to the previous, we're adding a new start state, which branches to the original start states under empty transition. And now this is an NFA for this language, A union AB. And lastly, now we're one step away from getting the star of this. And how are we going to do that? We're going to take this thing here and apply the construction for the star closure. And that's going to be an NFA which does A union AB star, which is what we wanted in the first place. So first we're going to bring that one down because we've already built that one. And now remember how we built the closure under star. We made the accepting states return back to the start state, and we added a new start state to make sure we got the empty string in there that transitioned to the original start state under epsilon. Okay, so that's all I wanted to say for today's lecture. Let's do a quick review. Very important concept, nondeterminism and nondeterministic finite automata. We proved they're equivalent in power, showed the class of regular languages closed under concatenation and star. We showed how to do conversion of regular expressions to NFAs. So I think that is it for today's lecture, and thank you all for being here. I'll try to answer a few of these. Why does concatenation have order? Well, because it's an ordered construction. Is there a simple way to prove closure under concatenation without using nondeterminism? No. Why are the empty strings at the except state? Can't they be at any state? Doesn't star make copies of any part of the input? No, it's only, you have to think about what's going on. You don't want to, you have to branch back to the beginning only on an except, because that means you found a piece that's in the original language. Is there an automaton that can add sum or subtract? Memory automata. Well, depends on what you mean by all that. But certainly there are more powerful machines that we're going to study than finite automata. But yes, there is, and even finite automata can add and subtract if you present the input in the right way. I refer you to the first problem on the homework. So I think I'm going to check out then. Take care, everybody. Bye-bye.